electrical and magnetic properties of materials. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video we're going to discuss electrical and magnetic properties of materials such as resistivity, capacitance, inductance, magnetization, and hysteresis through 16 exercises that frequently appear in exams for electrical engineers. Let's go to the first exercise. Exercise number 1. Design a power transmission cable 100 kilometers long that will carry a current of 200 amps with no more than 500 kilowatts of power loss in letter A and 50 kilowatts of power loss in letter B. Okay, my friends, this is the exercise. Let's solve it. Letter A. The maximum power loss needs to be 500 kilowatts, okay? The exercise said that the transmission cable is 100 kilometers long. And that it must carry a current of 200 amps. The cable needs to be able to support this current. This is the requirement of the exercise. To design such a transmission cable, we need to work on its resistance. Okay, let's calculate the resistance of the cable. Power is equal to resistance times current squared. This we know. This is the amount of power that will be lost as a function of the current. And using this expression, we can calculate the resistance of the cable. The power was said to be 500 kilowatts. This is the maximum power that may be lost along the length of the cable. And the current is 200 amperes. With this data, with this maximum power loss and the nominal current as 200 amps, the resistance of the cable shall be 12.5 ohms. Okay? Now, we need to calculate the cross-sectional area of the cable. Okay? The cross-sectional area of the cable. This is the other parameter that we are going to use to design this transmission line. The cross-sectional area of the cable is alright? This is the expression of resistance as a function of conductivity, or if you prefer, resistivity. And this is equal to 100 kilometers divided by the resistance of the cable that we just calculated, 12.5 ohms times the conductivity of the metal, the conductivity of the material that we are going to use to make the cable. But if we refer to a table, the conductivity is frequently given per centimeter. Then we need to pass kilometer to centimeter. And this gives a parameter such as 800,000 over sigma, which is the conductivity of the material. Alright? To design the cable, we are going to consider some metals. Let's consider three metals that have excellent electrical conductivity: aluminum, copper, and silver. If we refer to a table, we see that the conductivity of aluminum is 3.77 times 10 to the fifth Siemens per centimeter. The conductivity of copper is 5.98 times 10 to the fifth Siemens per centimeter, and the conductivity of silver is 6.8 times 10 to the fifth Siemens per centimeter. If we use these values of conductivity for each of the material, we're going to get that for aluminum, the cross-sectional area is going to be 800,000 divided by 3.77 times 10 to the fifth, and this gives 2.12 centimeters, square centimeters, okay? For copper, the cross-sectional area is going to be 800,000 divided by 5.98 times 10 to the fifth, which is equal to 1.34 square centimeters. And lastly, for silver, the cross-sectional area is 800,000 divided by 6.8 times 10 to the fifth, which is 1.17 square centimeter. And now we can calculate the diameter. The diameter for aluminum is going to be 2.12 centimeter square centimeter, equals to pi d squared over 4, which gives a value of 1.64 centimeters. The same is going to be done for copper and silver. For copper, it is going to be 1.34 square centimeters equal to pi d, which gives a value of 1.3 centimeters. And lastly, for silver, (1.17 square centimeters equals to pi d squared divided by 4, which is a diameter of 1.22 centimeters. Okay, these are the parameters of the cable. If we choose aluminum, copper, or silver, the cross-sectional area for aluminum is 2.12 square centimeter. The cross-sectional area for copper is 1.34 square centimeter, and the cross-sectional area for silver is 1.17 square centimeters, and the diameter for aluminum is 1.64 centimeters, for copper 1.3 centimeters, and for silver 1.22 centimeters. Okay. Now we are going to calculate the same for letter B, and in letter B we want a power loss at maximum of 50 kilowatts. Okay, let's calculate it all again, but with this parameter here instead of this. As we did before, we're going to calculate firstly the cable resistance. Now we have a maximum power loss of only 50 kilowatts. Fifty kilowatts divided by 200 amps squared is equal to only 1.25 ohms. Okay, a very small resistance for a 100 kilometer cable. Okay, and now we can calculate the cross-sectional area, provided that we already have the resistance of the cable. The cross-sectional area is going to be okay. We have here 8 times 10 to the 6th over sigma. This length is given in kilometers, but the conductivity is given in Siemens per centimeter. If we refer to a table, then we need to convert from 100 kilometers to 2 centimeters. Okay, we apply conversion to convert from kilometer to centimeters and divide by this resistance here, and with this we can calculate the cross-sectional area for different kinds of materials we are using in this exercise: aluminum, copper, and silver. Okay, and the cross-sectional area for aluminum is 8 times 10 to the 6th divided by the resistivity per centimeter of aluminum, which is 3.77 times 10 to the 5th, and this is equal to 21.2 square centimeters. For copper, divided by the conductivity of copper, which is 5.98 times 10 to the 5th Siemens per centimeter. Which is 13, gives a value of 13.38 square centimeter. And for silver, it is 8 times 10 to the 6th divided by 6.8 times 10 to the 5th, and this gives a value of 11.71 square 76 square centimeters for silver. From the cross-sectional areas, we can calculate again the diameters. For aluminum, using the same expression, we're going to use that area is equal to pi d squared divided by 4, and this gives a value for the diameter as 5.2 centimeters. For copper, 4.13 centimeters, and for silver, 3.87 centimeters. Okay? And what is our conclusion? What is our conclusion? Observe this diameter here, okay? This is huge. The thickness of this cable is very big. As copper and silver are too expensive for a 100 kilometers transmission cable, and since a cable of pure aluminum with a diameter of 5.2 centimeters would greatly sag under its own weight, it is infeasible to expect a cable to have only 50 kilowatts of a power loss over 100 kilometers. So, what should we do? We should expect a larger power loss than 50 kilowatts over 100 kilometers of line and a cable with a resistance of a little larger than 1.25. This is too small, okay? Practical cables have resistances greater than this. Also, to avoid sagging, cables are reinforced with steel at their core. Alright, my friends, this was exercise 1. Let's go to exercise 2. Exercise 2, mobility and the drift velocity of electrons in copper. Assuming that all of the valence electrons contribute to current flow, letter A, calculate the mobility of an electron in copper, and letter B, calculate the average drift velocity for electrons in a 10-meter wire when 50 volts is applied. Okay, my friends, this is the exercise. Let's go to the solution. Letter A. The valence of copper is 1. Consequently, the number of valence electrons equals the number of copper atoms in the material. Note, a valence of 1 means that copper has 1 electron in its valence shell. Okay? From a table, we find that copper has 8.466 times 10 to 22 electrons per centimeter cubed, or cubic centimeters. Since the mobility of electrons in copper depends on its conductivity and the electron charge, we can use this expression here. Mobility is proportional to the conductivity of the material divided by the number of electrons times the electron charge. And this is 5.98 times 10 to the fifth Siemens per square centimeter, which is the conductivity of copper, divided by the number of electrons in the material, times the electron charge, which is 1.6 times 10 to the negative 19, and this gives a mobility of 44.1 square centimeters per volt second. Okay? This is the result of letter A, where N is the number of electrons per unit of volume of copper, sigma is the conductivity of copper, and Q is the electron charge. Alright, let's go now to letter B. If the electrical field intensity is, we're going to use the expression of electrical field intensity. E is equal to V over L. Alright? And the exercises say that a voltage of 50 volts is applied over a wire of length equal to 10 meters, and this gives a value of 0.05 volts per centimeter. Okay? Finally, we can calculate the drift velocity using these results, and knowing that the average drift velocity is the mobility of electrons in the material, in this case copper, times the electric field intensity, and with our data it is 44.1 square centimeters over volt second times 0.05 volts per centimeter, and this is equal to 2.2 centimeters per second. This is the average drift velocity of electrons in copper. Okay, my friends, this is all for exercise 2. Let's go to exercise 3. Exercise 3, influence of temperature on resistivity. Calculate the electrical conductivity of pure copper at letter A 400 degrees Celsius and letter B negative 100 degrees Celsius. Okay? This is the exercise. Let's go to the solution. To calculate the conductivity, we're going to use the temperature-dependent expression of resistivity. Rho equals to rho RT times 1 plus alpha R times delta capital T, where rho RT is the resistivity at room temperature, which is 25 degrees Celsius. Rho R is the temperature resistivity coefficient, and delta capital T, this is the temperature difference, okay? Taken as a reference the room temperature, 25 degrees Celsius. If we refer to a table, we find that the resistivity of copper at room temperature is 1.67 times 10 to the negative 6 ohm centimeter. The temperature resistivity coefficient of copper is 0.0043 ohms per degree Celsius, and I think it is enough. Okay, we have all the data we need to calculate what the exercise wants us to calculate. Let's go to letter A. At T equal to 400 degrees Celsius. Okay? Then this expression here, if we substitute the variables by the values, we find that rho is equal to 1.67 times 10 to the negative 6 times 1 plus this was given as 0.0043 times 400. 400 is the temperature for which we're calculating this, and the reference is room temperature, which is 25 degrees Celsius, and this gives a value of resistivity of 4.363 times 10 to the negative 6 ohm centimeter. Okay, and this is not the final result yet. We do not want the resistivity. We are using the expression of resistivity, but in reality the exercise wanted us to calculate the conductivity, and the conductivity is the inverse of the resistivity. Therefore, the conductivity is going to be calculated as the inverse of the resistivity, which is equal to 2.29 times 10 to the 5th Siemens per centimeter. Likewise, we calculate for letter B. For letter B, we want at T equal to negative 100 degrees Celsius. We do the same. We apply this expression here, and it is going to be the resistivity at room temperature, which was given as 1.67 times 10 to the negative 6 times 1 plus the temperature resistivity coefficient, which was given as 0.0043, and the temperature is a negative 100 degrees, taking as reference the room temperature, which is 25 degrees Celsius, okay? We are calculating in Celsius. And by carrying out this multiplication here, we find that the resistivity at negative 100 degrees is 7.724 times 10 to the negative 7 ohm centimeter. And if we invert this, we find the conductivity. The conductivity is therefore 1 over rho, which is 12.9 times 10 to the 5th Siemens per centimeter. Okay, my friends, this is how we calculate conductivity using the expression of resistivity when we want to assess the resistivity of one material. In this case here it was copper, pure copper, okay? And this is temperature dependent. We depart from one temperature and arrive at another temperature. Here it was 400 degrees, and here negative 100 degrees. Okay, this is all for exercise 3. Let's go to exercise 4. Magnetization saturation in iron. Exercise 4. Calculate the theoretical magnetization limit for iron. Compare this value with the 2.1 Tesla observed experimentally. Okay, my friends, this is the exercise. Let's go to the solution. If we refer to a table, we observe that the number of iron atoms per cubic meter is 8.496 times 10 to the 28th is the number of iron atoms per cubic meter, and the maximum volume magnetization for iron is the magnetization saturation for iron is 3.15 times 10 to the 6th ampere per meter. Okay? And note that magnetization represents the increasing flux density due to the core material, alright? It is measured as the magnetic flux density is equal to μ times the magnetic field intensity plus μ times m. Okay, where m is the magnetization, and this is the magnetic permeability in free space. And we can rewrite this in this way. B is equal to μ h 1 plus xm, okay? Which is equal to the permeability of free space times the relative permeability of the material times the magnetic field intensity, H. Alright? Where mu R is the relative permeability of the core material. And here we can infer that they are equal. The relative permeability is equal to 1 plus Xm, where Xm is the magnetic susceptibility of the material. Since for iron, the relative permeability of iron is big, okay? This is what we are going to infer with this theory here. Since for iron, this is much greater than this. Since for iron, this is much greater than this, what does it mean? This means the magnetization, this means a magnetic density without a core. In free space, for example, this is a magnetic flux density without a core. But when you put an iron core, you are going to greatly increase the magnetization because the relative permeability of iron is big, okay? Since this is true, we can write that for iron, the magnetic flux density is proportional and approximately equal to O times M. This is the theory, okay? Now we are going to use the numbers to calculate the theoretical magnetization limit for iron. Therefore, the saturation flux density in Tesla is given by this set is going to be equal to the magnetic permeability of free space, which is 4 pi times 10 to the negative 7 Weber per ampere meter times 3.15 times 10 to the 6th ampere meter, and this gives a magnetic flux density saturation of 3.96 Tesla. Okay, and the exercise wanted us to compare this result with, this is the theoretical and this is the practical limit. Okay, this theoretical value is almost twice the experimentally observed value of 2.1 Tesla. This difference is due to how atoms behave individually and in the crystalline. It can be shown that for iron, the difference is due to the 3D electron orbital moment being quenched in the crystalline. Okay, my friends, this is all for exercise 4. Let's debate now exercise 5. Material selection for a solenoid. Exercise 5. Select a material for the production of a coil with a flux density of at least 0.2 Tesla when a 10 milliamperes current flows through the conductor. Due to space limitations, the solenoid should have a turns density of 1000 turns per meter. Okay, my friends, this is the exercise. Let's go to the solution. Firstly, we are going to determine the magnetic field produced by the solenoid. Okay? The magnetic field produced by the solenoid is going to be the magnetic flux intensity, can be calculated using this expression, N over L times I, where N over L was given as 1000 turns per meter. Okay? 1000 turns per 1 meter, and a current of 0.01 amps. Therefore, the magnetic field intensity is going to be 1000 turns per meter times the current. And this gives a value of 10 amperes per meter. Alright? If the flux density must be at least 0.2 Tesla, then the permeability of the core will be, we are going to use the flux density to calculate the permeability of the core. We know that the magnetic flux density is equal to mu times H. The magnetic flux density is related to the magnetic field intensity by the permeability of the material. Okay? Then we calculate the permeability as B over H, which is equal to 0.2 Tesla divided by 10 amperes per meter, and this is equal to 0.02 Weber per ampere meter. Okay? The relative permeability of the core material must be at least due to space limitations, the solenoid should have a turns density of 100 tons per meter. And now we are going to calculate the relative permeability of the core based on this data. Okay, the relative permeability, we know that mu is equal to mu r times mu O. This is the magnetic permeability of free space, and this is the relative permeability of the core material, and the multiplication between them gives the permeability of the material, or permeability of the core. Using this expression, we find that the relative permeability of the material must be at least 15,915. Okay, the relative permeability of the core material must be at least 15,915 for the conditions established by the exercise. The magnetic flux density of at least 0.2 Tesla when a 10 milliamps current flows. Okay? And if we refer to a table, we may observe that the grain-oriented silicon ion has a maximum relativity of 50,000 and may represent a good choice for the core material. Okay? We can choose any kind of material. I'm suggesting grain-oriented silicon ion for this core material. Okay, this is all for this debate of exercise 5. Let's go to exercise 6. Current and current density. Exercise number 6. Given the vector current density 10 rho squared z a rho minus 4 rho cosine squared phi a phi amperes per square meter. Letter A, find the current density at the point P. And letter B, determine the total current flowing outwards through the circular band. Okay, this is going to be the circular band. Okay, this is the element of urea, ds, and the band is bounded by this rho equal to 3, phi from 0 to 2 pi, and z from 2 to 2.8. Okay, this is the exercise. Let's go to the solution. For the A, substituting the values, okay, here, we substitute these values here. Here, we find that J is equal to 10 times 3 squared, because rho is 3, times 2, because z is 2, in the a rho direction, minus 4 times 3 times the cosine squared of 30 degrees in the a phi direction, amperes per meter, amperes per square meter. Okay, and ultimately we find that J is equal to 180 in the a rho direction, minus 9 in the a phi direction, amperes per square meter. Okay, this is letter A. Now let's calculate letter B. In letter B, we're going to use that I is equal to the double integral, or if you prefer, the surface integral of J ds. J is this, okay? ds is this. And we are going to take the dot product of these two vectors here, this and this. In reality, this is a vector as well. Alright? It is going to then be equal to the double integral, or if you prefer this, the surface integral of 10 rho squared z a rho minus 4 rho cosine squared phi a phi in a dot product with rho d phi dz in the a rho direction. And if we carry out this dot product here, we find that I is equal to the double integral of 10 rho cubed z d phi the Z for rho equal to 3, okay? And we just need to solve this integral respecting the limits of integration here. Okay, I is equal to 270 from 0 to 2 pi in the phi direction, from 2 to 2.8 in the z direction, z dz d phi, and this gives a value of 3,255 amps. Okay? Letter A is this, letter B is this. Okay, my friends, this is all for exercise 6. Let's go to exercise 7. Exercise number 7. Find the resistance of a 1 mile length of copper wire which has a diameter of 0.0508 inches. Okay, this is the exercise. Let's go to the solution. First of all, we are going to carry out unit conversion. We are going to pass from miles and inches to meters. Okay, firstly, the diameter. It was given as 0.0508 inches. We are going to pass it to meters. 0.0508 inches times 0.0254 meters per inch. And we find 1.3 times 10 to the negative 3 meters. With this value, we can find the cross-sectional area of the copper wire. The cross-sectional area is pi d squared over 4, which is equal to pi times 1.3 times 10 to the negative 3 meters squared over 4. And this is 1.31 times 10 to the negative 6 square meters. And passing the length from mile to meters, 1 mile is equal to 1,609 meters. Referring to a table, we find that the conductivity of copper is 5.8 times 10 to the 7th Siemens per meter. With this data, the resistance of the wire can be calculated as R is equal to length divided by conductivity times cross-sectional area. And if we use the values, for length we use 1,609 meters. For the conductivity, we use 5.8 times 10 to the 7th Siemens per meter. And the cross-sectional area, we use 1.31 times 10 to the negative 6 square meters, and we find a value of resistance of 21.2 ohms. Okay? This wire can safely carry about 10 amperes DC, corresponding to a current density of, calculating the current density, 10 amps over the cross-sectional area, 1.31 times 10 to the negative 6 square meters. We find a current density of 7.65 amperes per square millimeter. With this current, the potential difference between the two ends of the wire is 212 volts. How do we calculate the voltage or potential difference between the two ends of the wire? We simply multiply the current, 10 amps, by the calculated resistance, which is equal to 212 volts. The electric field intensity can be calculated using this voltage here. We know that the electric field intensity is equal to voltage divided by length, which is equal to 212 volts divided by 1609 meters, and this gives a value of 0.312 volts per meter, or if you prefer, 0.00312 volts per centimeter. Okay? We can calculate the derivative velocity as well. The derivative velocity can be calculated using this expression. The average derivative velocity can be calculated as the mobility of electrons in copper times the electric field intensity. And we calculated already in a previous exercise, we know that the mobility of electrons in copper is 44.1 square centimeters over volt squared. And that's why I passed from meter to centimeters, because he is given in square centimeters. Then we just multiply this value by this, 0.00312 volts per centimeter, and we find an average derivative velocity in copper as 0.137 centimeters per second. Okay? If we apply this voltage here, 212 over a length of 1609 meters, the average derivative velocity of electrons in copper in this material is going to be 0.137 centimeters per second. Okay, this is what the exercise wanted us to calculate. The exercise wanted us to calculate the resistance, but with this data we extended our debate to the voltage, to the electric field intensity, and this data can be used to calculate the average derivative velocity as well. Okay, so we calculated even more than what the exercise wanted. Let's go now to exercise 8, my friends. Dielectric materials. Exercise 8. Calculate the capacitance of a parallel plate capacitor having a mica dielectric of permittivity equal to 6, a plate area of 10 square inch, and a separation of 0.01 inches. Okay, my friends, this is the exercise. Let's go to the solution. Okay, let's calculate to calculate the capacitance, we're going to use this expression here. The capacitance is equal to the permittivity times the cross-sectional area divided by the separation. The cross-sectional area was given in inches. It was given as 10 square inches, and the separation was given also in inches, 0.01 inches. Before calculating and before using this expression, we are going to carry out unit conversion. For the cross-sectional area, we are going to do the following. A is going to be 10 inches, 10 square inches. The exercise gave the cross-sectional area in this way, times the unit of conversion, .0254 meters per inch. Okay, this is how we convert from inches to meter. But as it is in area, as it is a area, we have to square it. It's going to be squared, and this unit conversion results in 6.45 times 10 to the negative 3 square meter. And for the separation of the plates, we do the same. The separation was given in inch. We use this conversion here. But we are not going to square it because the separation is not squared, only the cross-sectional area. And we find this number here. Okay, now after carrying out this unit conversion, we can use the expression. Then we use this. C is equal to 6 times the permittivity of mica. Is going to be, this is the relative permittivity. The electrical permittivity of mica is 6 times 8.85 times 10 to the negative 12 farad per meter, which is the permittivity of free space, times 6.45 times 10 to the negative 3 square meter divided by the separation, which is 2.54 times 10 to the negative 4 meters, and this gives a value of 1.35 nanofarad. Alright, my friends, and there is a note. A large plate area is obtained in capacitors of small physical dimensions by stacking smaller plates in 50 or 100 decker sandwiches, or by rolling up foil plates separated by a flexible dielectric. Okay, my friends, this is all for exercise 8. Let's go to exercise 9. Mutual inductances. Exercise number 9. Calculate the self-inductances of and the mutual inductances between two coaxial solenoids of radius R1 and R2 with R2 greater than R1 carrying I1 and I2 with N1 and N2 turns per meter respectively. Okay, the coaxial solenoids have radius R1 and R2 and they carry currents I1 and I2. Alright, this is the exercise. Let's go to the solution. Well, within the solenoid, we can confidently say that the magnetic field intensity is okay. You can imagine a solenoid, and deep within the solenoid, the magnetic field intensity is given by this expression here. And N1 is going to be equal to N divided by D. Alright, this is the turns density of a solenoid. And in this way, we can calculate the magnetic field intensity using the data provided by the exercise. And this is N1 times the current in the AZ direction. Okay? Similarly, we can find for solenoid 2. For solenoid 2, this is going to be for solenoid 1. For solenoid 2, we can do the same and find that it is N2 times the current. Here is current 1, here is going to be current 2 in the AZ direction. Alright? And now we are going to calculate the flux and the flux density. We know that the flux can be calculated using this expression here. The magnetic flux density in a dot product with the differential of area. And if we assume that they are perfectly aligned, then we can find that this is equal to this. Simply, this integral assumes the simplest form. And since B is equal to mu H, the magnetic flux density is related to the magnetic field intensity by the permeability of the material. We can say that phi is equal to B A, which is equal to mu 0 or mu O times the cross-sectional area times N times I. And if we substitute for solenoid 1, they are coaxial solenoids, one within the other. And if we substitute for solenoid 1, we are going to discover that phi 1, 2 is equal to mu 0 times N1 times I1 times the cross-sectional area, which is pi r1 squared. And it turns out that if we substitute for the current, okay, imagine that this is the influence, this is the influence of solenoid 1 and solenoid 2. We find that the mutual inductance is M12 is equal to N2 over I1 times phi 12, which is equal to M21. Applying this here, we find that the mutual inductance is nu O times N1 times N2 times pi R1 squared. Okay, this is the expression that we are going to use. Now, using numbers, these numbers here is provided by the exercise, we can say that the mutual inductance, okay, one has to be equal to the other, is equal to 4 pi times 10 to the negative 7, which is the permeability of a free space times the turns density, which is here for solenoid 1, 5,000 turns per meter times 8,000 turns per meter times the cross-sectional area, which is pi times, for we are going to use this radius here, which is 0.02 squared. And this gives a value of mutual inductance as 0.0632 Henry per meter. All right? And this is the mutual inductance. Now we are going to calculate the self-inductances. Okay, the self-inductances can be calculated using the flux. Okay, the flux in one created by the passage of current in solenoid 1, okay, the self-inductance, the inductance that it creates in itself, is equal to mu O N1 I1 pi R1 squared. And since the inductance is related, to the flux in this fashion here, we simply multiply this by this, and we find that it is no zero N1 squared A1D. But if we want the inductance per unit of length, we divide this per meter, and we find that L1 is equal to this okay, N1 squared A1D. All right? Henry per meter. This is, because of this capital N here, this is the entire inductance, and this is the inductance per unit of length per meter. Substituting the values, we find that L1, substituting the values here, we find that L1 is equal to 0.395 Henry per meter. And in a similar way, using this expression, we find that L2 is equal to mu O N2 squared times A2, which is equal to 22.7 millihenry per meter, or if you prefer, 0.227 Henry per meter. Okay, my friends, these are the values of the mutual and the self-inductance. And it is all for exercise 9. Let's go to exercise 10. Exercise 10, a parallel plate capacitor has circular plates of 8.2 centimeter radius and 1.3 millimeter separation. With this data, the exercise wants us to calculate in letter A the capacitance, and in letter B what charge will appear on the plates if a potential difference of 120 volts is applied. Okay, my friends, this is the exercise. Let's go to the solution. In letter A, we want to calculate the capacitance, and to calculate the capacitance, we need to use this expression here. We are assuming that the dielectric is free space, okay? That's why we are using the electric permittivity of free space. This A here is the surface area of the plates, and the D is the separation, okay? Using this data, we will find that 8.85 times 10 to the negative 12 farads per meter is the electric permittivity of free space, times pi times the radius squared, 8.2 times 10 to the negative 2 meters squared. It was given that the radius of the circular plates is 8.2 centimeters, and the separation is 1.3 millimeters. We convert it to meters, and it becomes 1.3 times 10 to the negative 3 meters. In this way, carrying out this multiplication and division, we find a capacitance of 140 picofarad. Now in letter B, we want to apply voltage of 120 volts, okay, to measure the charge. Q is equal to CV, which is going to be equal to 140 picofarad times 120 volts, and we find a charge of 17 nanocoulombs on the plates of the capacitor. Okay, my friends, this is exercise number 10. Let's go to exercise number 11. Capacitances in series and in parallel. Exercise 11. For the circuit of the figure, find the equivalent capacitance if, let's put the data here, C1 is equal to 10 microfarad, C2 is equal to 5 microfarad, and the C3 is equal to 4 microfarad. Okay? So, how do we solve this? Okay? Before solving, it is fundamental that we understand the possible combinations of capacitance. Okay? Let's imagine here capacitances in parallel. Alright? And here is C1, C2, C3. There is going to be a current here, I'll call I, and there is going to be a voltage here, I'll call E. And here, there will be one current, one current, one current. Okay? Our conclusion is that I is equal to I1 plus I2 plus I3, and so on. I1 passes in the first capacitor, I2 passes in the second capacitor, I3 passes in the third capacitor. Okay? But you can see here that the same voltage is applied on every one of them. Alright? We are going to use this feature to calculate the equivalent capacitance. Okay? We know that for a capacitance, the impedance in the frequency domain is 1 over SC. Okay? In the frequency domain, the impedance of the capacitance is this, or the reactance if you prefer. Let's generalize and say that the impedance of the capacitance. Okay? Then we have here E over ZC plus ZC1, E over ZC2 plus E over ZC3, and so on. We are going to factor out this E to isolate E, and we find that E is equal to 1 over. Substituting this by this, we get that it is 1 over SC1 plus 1 over SC2 plus 1 over SC3, and so on. Okay? 1 divided by 1 over SC is SC. Then it becomes SC1 plus SC2 plus SC3, and so on. And here we have E multiplying them all. We have here E multiplying them all, as here. Alright? We carried out this division here and we discovered this. Then we pass this to the other side. It becomes E over I equal to 1 over SC1 plus C2 plus C3 plus, okay? But E over I is already the equivalent capacitance or the equivalent impedance, okay? Voltage divided by current is impedance. Then 1 over SC equivalent is equal to 1 over SC1 plus C2 plus C3, and so on. And what is the conclusion? The conclusion is that for the parallel connection, C equivalent is equal to C1 plus C2 plus C3 to the end. All right, this is the parallel connection. Let's put a parallel here. And in a similar process, we can verify that for the series connection, okay, I'm not going to do it here. I'm going to let you try it in your house or in your office. And for the series connection, we know that for the series connection, I'm going to put a plus there. For the series connection, we do this 1 over C1 plus 1 over C2. No. 1 over is this plus 1 over C3 plus. This is the series and this is the parallel connection. Okay? With this result, we can calculate what the exercise wanted us to calculate. The equivalent capacitance for the 1, 2, and 3 will be equal to the series connection between 1 and 2 and the series connection between these two in parallel with the 3, okay? C3. When they are connected in series, we apply this rule here, okay? So C equivalent to is going to be C1, C2 divided by C1 plus C2, okay? When there is only 2 in series, we use the product over the sum, and we get that using these values here, we find that it is 3.333 microfarad, and adding the capacitance in parallel, we find that C equivalent 1, 2, 3 is 7.333 microfarad, okay? You may be thinking of it as strange because it is the opposite for resistors. When there are resistors in series, we add, and when they are in parallel, we apply this. But for capacitors, it is the opposite. When they are in series, is going to be this expression, and when they are in parallel, we use this expression here, okay? That's why I brought this for our debate, because it is different. Alright, it is all for exercise 11. Let's go to exercise 12. Induced voltage caused by mutual coupling. Exercise 12. Two coils have mutual inductance of 325 microhenry. If the current in the first coil increases at a uniform rate of 830 amperes per second, letter A, what is the magnitude of the induced electromotive force in the second coil? And letter B, what would be the EMF if the current is 830 times the cosine 2 pi 60 hertz times t? Okay, my friends, this is the exercise. Let's go to the solution. In letter A, we need to calculate the magnitude of the EMF in the second coil for a current growing at a uniform rate of 830 amperes per second. All right? V2 of t is equal to minus m times the derivative with respect to time of I1 of t. Okay? There is a mutual coupling, and the I1 is going to cause a voltage on the second coil, And using the data, we find that it is negative 3.25 times 10 to the negative 4 Henry times 830 amperes per second. And this gives a voltage of negative 0.27 volts. Okay? It was easy. You just apply this. Okay? And this here, observe that the derivative of this is this, okay? The derivative of a constant times t is the constant. And multiplying, we get this, okay? It was easy. Now let's go to letter B. We are going to do the same. Now I of t is 830 times the cosine of 2 pi 60 hertz times t. Alright, V2 of t is going to be equal to negative 3.25 times 10 to the negative 4 Henry times the derivative of this 830 times the cosine 2 pi 60 hertz times t. Okay? If we take the derivative, okay, observe that the derivative of the cosine is negative sign. Alright? Then it is going to be V2 of t equal to negative 3.25 times 10 to the negative 4 Henry times negative 312 910 times the sine 377 t, okay? If we multiply this, we get 377. And multiplying this by this, we get that V2 is equal to 101.7 times the sine of 377 times t, okay? This is the answer of letter B, and it is all for exercise 12. Let's go to exercise 13. Exercise 13 now. A heating element consists of two wires of different materials connected in series. At 20 degrees Celsius, the two wires have resistances of 600 ohms and 300 ohms and average temperature coefficients of 0.001 per degree Celsius and 0.004 per degree Celsius respectively. With this data, what is the heating element's total resistance at 50 degrees Celsius? Okay, this is the exercise. Let's go to the solution. The resistances were given for 20 degrees Celsius. To find the resistance for 50 degrees Celsius, it is necessary to use the temperature-dependent resistance formula. Okay, we are going to use that R is equal to RO 1 plus alpha delta T. Okay? This is the expression that we are going to use for wire A. RA is equal to RO 1 plus alpha A T minus T0. Okay? For wire A, RO is 600 ohms. Use here 600 ohms. Here it is 0.001 per degree centimeter. We're going to use it here. The final temperature is 50 degrees. We're going to use 50 degrees here. And here we're going to use 20 degrees because it is the initial temperature. And if we use all these values and calculate, we find 618 ohms. The same is going to be done for wire B. We use that RB is going to be equal to, okay, now I am going to use the values just to show you the initial resistance of wire B was given as 300 ohms. Multiplying 1 plus alpha B is 0.004 per degree Celsius times 50 degrees Celsius minus 20 degrees Celsius, and this gives a resistance of 336 ohms. Okay? Therefore, the total resistance of the heating element R dot is equal to the sum. You sum this with this and you find 954 ohms. Okay, and this is the answer, the solution of exercise 13. Let's go to exercise 14 now. Exercise 14, a solid cylindrical copper conductor has a length of 1,000 meters, a resistance of 0.225 ohms, and a resistivity of 1.77 times 10 to the negative 8 ohm meter. With this data, calculate the diameter of the conductor. This is the exercise. Let's solve it. To find the diameter, we're going to use the resistance formula to calculate the cross-sectional area. Okay? We know that R is equal to L over A times rho. Okay? With this expression, we find that the cross-sectional area is rho L over R. And this is 1.77 times 10 to the negative 8 rho ohm times 100 meters, 1,000, immediately 1,000 meters divided by the resistance. The resistance is 0.225 ohms. Calculating, we find a cross-sectional area equal to 7.87 times 10 to the negative 5 square meters. Subsequently, we use the expression of area given the diameter, and we find that the diameter is 4a over pi, the square root of 4a over pi. Using the values, we find, applying here this value here, pi we know, we find that it is equal to 10.01 millimeters. Okay, this is all very simple. This is all for exercise 14. Let's go to exercise 15. Exercise 15. For operation at 60 Hertz in a given peak flux density, the core loss of a given core is 1 watts due to hysteresis and 0.5 watts due to eddy current. With this data, estimate the core loss for 400 Hertz operation with the same peak flux density. Okay, my friends, that's the exercise. Let's go to the solution. Assuming constant peak flux density, power loss due to eddy currents increases with the square of frequency. Alright? It is important to understand this, that the power loss due to eddy currents increases with the square of frequency, and the power loss due to hysteresis is directly proportional to frequency. Okay? P2 is equal to P2 hysteresis plus P2 due to eddy current, in which this is directly proportional to frequency, and this increases with the square of the frequency. All right? Then P2 is going to be P1 for hysteresis, P1 F2 over F1, okay, plus P1 eddy F2 over F1 squared. All right? P2 hysteresis is equal to P1 hysteresis, but it is directly proportional to frequency. P2 eddy is equal to P1 eddy, but it increases with the square of the frequency. Knowing this, we can confidently say that P1 hysteresis is 1 watt. The exercise gave this. F2 is 400 Hertz. F1 60 Hertz. P1 eddy is 0.5. 400 Hertz divided by 60 Hertz, but here squared. Calculating, we find P2 equal to 28.88 watts. All right? As we increase the frequency, core losses increase greatly. This is all for exercise 15. Let's go to the last. Let's go to exercise 16. The last exercise, a theoretical one. What considerations are important to minimize losses due to hysteresis and eddy currents? Okay, let's go to the solution. Hysteresis. Firstly, let's debate hysteresis. Hysteresis. To minimize the loss due to hysteresis, we should select a material having a thin hysteresis loop, such as this. This is a thin hysteresis loop. or other applications, transformers and motors. On the other hand, for a permanent magnet, we should choose a material with a wide hysteresis loop, such as this one. What is hysteresis? When a DC current is applied to a coil having an iron core, the material's magnetic domains align in a single direction. To reverse the direction of the domain alignment, current of opposite direction must be applied. Okay? We need to spend energy to realign the domains. In an AC system, domain alignment reversal occurs proportional to the system's frequency, and energy is lost in domain realignment. Okay, that's why we lose energy in hysteresis. Now let's talk about eddy currents. To minimize losses due to eddy currents, the core is laminated into thin sheets of metal. Alright, my friends, this is all for exercise 16, and this is all for this video. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number. Guys, goodbye.